Let's begin. Today we will start a new chapter in our pursuit of catching up with engineering analysis. The topic is going to be on partial differential equations and the great conservation laws. So I will touch on conservation laws, not too much from a physics perspective, just enough physics to help you develop intuition, but I will lean hard on the math. And it's really not that difficult once you figure it out once you do the work a couple of times by hand, it will just sink in your mind. Then you can relate the math to the physics. Then next semester with Professor Sutherland and Professor Yachao, you'll lean more into the physics and how the math can describe different physical situations. We will also be quite hands-on. So as much as I like to be mathy, if I want to be too deep in math, I'd rather use a board, and makes it hard when we have an online mixed class. And I also want to be practical. So I want you to know how to build a vector field or visualize a vector field and do an animation of a two-dimensional contour plot in Python, right? So we will spend time on those as well. We'll still keep the math as rigorous as we can without having to go into lemmas and theorems. We rely on the mathematicians who have proved all of those things for us. So this will mostly be a reminder, but also a refresher or a new introduction. And for those who, if you are familiar with this stuff a lot, just bear with me because I will give you a different interpretation that possibly you might not have heard of before, or you might have a better interpretation that I'd welcome for you to come and share with me after class. And I love quotations and things. It's like when you age, you become like cheese, like aged cheese. You want to come up with like fancy sentences and words like that. So I'll talk about this in Intro to Research and the seminar this Friday as well. But if PDEs, remember I said the PDEs, or differential equations, are the tuning forks of science, and tuning forks essentially resonate with the basic fundamental frequencies. And so if PDEs are the tuning forks of science, then vector algebra and calculus are the tuning forks of PDEs, right? So we're going to have like an infinite regression of tuning forks, but they're like the language of partial differential equations, also the tuning forks of PDEs. So you cannot develop PDEs without vector calculus. I know that seems strange, but most interesting PDEs are at least 2 or 3 dimensional in space, and they have a time dependence. Once you hit 2 or more dimensions in space, you have to start using vectors and tensors. And the things we will learn about are scalar and vector fields, what we mean by a field, things that change in time and space. And we will dig deeper into the calculus side of, we will look at some vector algebra, just quick reminders, vector addition, multiplication, etc. And we will look specifically for the calculus where there's change, right? So when you think calculus, you're talking derivatives and integrals. We will look at gradients, divergence, and curl, specifically, and then relate those to the great integral theorems, divergence and gradient theorem, the divergence and gradient theorems, because those will be very useful in converting partial differential equations from an integral form to a differential form. I come from a school of thought that, we will hit that, we will talk more about that when we talk about PDEs. I come from a school of thought that believes that the true mathematical description of physical phenomena can only be done in integral form. Because integral forms do not care about discontinuities locally, because you're integrating, you're smoothing everything over a region of space. Think of a shock wave, for example. You have a local discontinuity in pressure or density. Numerically or analytically, the function is not defined there. No derivatives are defined as you go through a shock wave, right? It's this Heaviside step function. But with integrals, an integral doesn't care. You can integrate over that shock without any issues whatsoever. Because of these theorems, like this theorem, for example, tells us that I don't really need to know about what's going on inside the volume. All I need to know is what's going on around the surfaces of that volume. So there you go. I can put a volume around a shock, and define an integral like this to compute a property, and all I care about is what's coming in and what's leaving without having to worry about what's going on inside the shock. Whereas the differential forms, you have to go pointwise. Now, and secondly, it's much easier to derive the integral forms of the equations of the conservation laws rather than going to the differential form. Has anyone done a shell balance before? Like take an infinitesimal volume, etc. Okay, great. So that's the differential analysis. But it's not very rigorous because you have to make a lot of assumptions, like why is it this way, why is it not that way? The integral form obfuscates all of that. You don't need that. And the best part is, once you have the integral form in one line of mathematical reasoning, you can convert from integral form to a differential form. So we will follow that path. There will be a few shell balance analysis, differential analysis here and there. But you'll be exposed to all of these ideas. We will start with scalar fields. And I'll define this as a scalar field is simply assigns a single numerical value, a scalar, a single value, to every point in a region of space representing a physical quantity that does not have a direction. So temperature, pressure, they have no direction. I know we say the word pressure force. What's the difference between pressure force and pressure? Okay, why? How is the pressure force obtained from the pressure? So the pressure has no direction. If I stand this way or stand that way, I still have the same atmospheric pressure acting on me, right? Right? Or here, there's no direction. If I lie this way, any plane you put, it's got the same point pressure. What is the pressure force? The pressure force is when you define a surface, okay, and then put the pressure on it, then the pressure becomes normal to that surface, and then the resultant force is what the pressure force is. So we will see that specifically for the pressure, you cannot define a pressure force unless you define a surface that the pressure is acting on. So we'll see that once we hit the Navier-Stokes equation. But we say with scalar fields, so these scalar fields, they change in space, but they can also change in time. So I forgot to put time over here. But they have a single value. They're just singular value, they're scalars. For example, this is a scalar field in one-dimensional space. Okay? This is also a scalar field in one-dimensional space. So they both change in space, right? But that's a scalar field in one-dimensional space. The best way now, if you want to add time, the best way to visualize the time dimension is to do an animation. Because time, we always feel that space is static, but time moves on. So the way you describe this when you're visualizing things is to actually do an animation. So for example, this is an animation of e to the minus t cosine x, e to the minus t, e to the minus x cosine x, actually. And you see kind of how it decays, right? So the time dimension is changing per frame. It's changing the value. It's still a scalar field in time and space. But the time dimension, I didn't draw it. I put it in an animation. Okay, so the time dimension is hidden in this plot, but as it changes the values of this scalar field. This is another scalar field that's dependent on time and one space dimension. This is the advection equation. I have this initial condition information, could be some temperature or some concentration, and I'm blowing air from the left, and it's moving to the right. So it's going to move like this, and it's going to change and then exit. Okay? So that's also a scalar field. Right? So we know how to do 1D plots, etc. Now what's more interesting are the scalars that are in 2 or more dimensions. So I will reserve the word dimension for spatial dimension. All right? So we can call the time dimension, but really we're going to hide it in an animation. Okay? What we will visualize are space dimensions. So here's, for example, a bimodal Gaussian function. It has 2 modes or 2 humps in it. And the first one is a little larger than the second one, and they each have could have a different standard deviation. Your initial reaction when you see a function like this, you see, oh, this is going to be a 3-dimensional plot because I have x and y on the plane, and the height of the function, I have to represent it as a value in the z direction. So your immediate reaction is to do a 3-dimensional surface plot. It looks pretty, but that's about it. I can say nothing about this. I can't even tell, like just kind of from looking at it, like what's going on behind the hump? Is it the same width? I don't know, like what's going on here? Is it going up? So whenever I see a 3D plot of a two-dimensional function, so this is 2 dimensions, there's only x and y, the z dimension is what pushed us to do a 3-dimensional plot. But we don't have to, because we can use color as our 3rd dimension. We can use color to designate height. And oftentimes, whenever I see a 3-dimensional plot, I immediately tell the authors or the student who's presenting, I was like, please give me a 2-dimensional contour plot. We cannot reason with 3-dimensional plots. We can't. We just can't. They're hard to see unless you're able to spin it around and zoom in, which you can't. I can't do that here. Right? I cannot touch it and unless I give you like a mock-up model of it, like a 3D printed version, then okay. But otherwise, don't do a 3-dimensional plot. Okay? Don't do a 3-dimensional plot. Now, we will talk about 3-dimensional fields. There's another way to render 3-dimensional fields. But even for 3-dimensional fields, you should take slices of the truly 3-dimensional field and do contours on those slices. 2-dimensional plots are the easiest to visualize. So instead of this, what if we squish these hills, or you might have a trough, squish them into the xy plane, and use color as your 3rd dimension. Use color to designate height. Okay? So that's what we can do here. That will result in what's called a contour plot. Okay? You can fill those contours or put lines on them. Now, you will see there's a color map usually associated with each plot that designates a value. Most of the time we're used to blue being cool or low and red being hot and high. And that's a good build on that intuition that people have. What is important in a contour plot is the color map, because the color map is going to tell you the value of the function that you're looking at. So in this case, now I can see, okay, so this is at its peak height, this is about 1 height. This one corresponds to this value, maybe about 0.5, I would say. You can put more points on your color map. You can kind of refine and put more contours, but you see the point. This one is easy to think about, is easy to navigate, and if you have a good tool to manipulate contour plots, you can click with your mouse or cursor and get values. And you can also assign, you see that like all of these circles here, they have the same value. So those are your contour lines. So typically a contour plot could be filled like this, or instead you would put contour lines with the color or without the color and assign values on those contour lines. So more to come. And as you write your first paper, you will be faced with things like this. Think of it this way. What is the cleanest way I can communicate my information that is simple, that is clear? Like if it were me here, I wouldn't put 700 contour lines. They're going to be all on top of each other. They will destroy your story. What about, what did I do here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 levels. That's good enough. And if I put a contour line, I'm not going to put a text on each contour line, because then all the text is going to be cluttered. I would put a text on every other contour line, for example, right? And the text would correspond to the value. Let's say this one would be 1, this one would be 9, this one would be 8, right? So I would go put 1, 0.9, 0.8. So I would put 1 here, and then maybe on the orange one, 0.7, maybe on this one. So people get an idea, right, without cluttering your graphic. Okay, don't just rush to the most. Your plots should not be dense, should not be obfuscating of what you're trying to communicate. It is always better to communicate a limited set of information really, really well than try to communicate a lot of information poorly. Okay? So in programming, we have this mantra that says, it's better to have no documentation than poorly written documentation. I'd rather have no documentation of a function than a crappy written or undescriptive documentation of a function. Okay? Same thing here. This is another function. Now look at, this is called the Taylor vortex. This is a common, this is the stream function of the Taylor vortex. We will learn these words also. This describes, it's a solution to the Navier-Stokes equations, actually. This is a solution to the Navier-Stokes equation. This is an incompressible flow. If you plot it in 3D, this is what you get. Can you see anything from this? I cannot see. Good answer. Thank you. Okay. Yeah, I can't see anything from this. It just looks, oh, it did a 3D plot. Okay, who cares? Now this, I can tell there's red and blue, and these are symmetric, right? The values are symmetric, from -1 to 1, and you see kind of the values here, and you see them, they're alternating. It's a very interesting flow field, okay? And you can reason with this better than just doing a 3D plot, okay? All right, so shall we do this together in Python? All right, let's Pythonify the heck out of this. Grab your notebooks. Now, every time I do a 3D plot, I have to jump on Google or Stack Overflow or ChatGPT or Gemini to help me with the latest and greatest. It's okay if you do that. What's more important is knowing what you need to do. You are in search of a contour plot, okay, or contour lines on a contour plot. How do I do that? How do I add labels to my contour lines? Go and Google it. There's 1,000 ways to present these, different color maps, for example, different levels, etc., right? So I cannot teach you all of those, but what I can teach you is what to look for, what you need to do, okay? So let's do this. We grab a Python notebook, and okay. 2005, what am I, dinosaur? Fall to 2025. Scalar fields, fall 2005 in class. That's in class. Okay, so let me get my boilerplate here. Okay. So all I need right now is this. We will talk about animations. I'm hesitant to talk about animations right now because there's many ways to do it. The way I personally like is to just export a series of images from the plot, and then in my operating system use a movie maker, like if you're in a Linux-based system like FFmpeg or Convert or ImageMagick. Just do the animation like that. That's my preferred method because then I can control quality, frame rates, and I don't have to bog down the Jupyter Notebook. So let me think about a way I could teach you a couple of tricks of doing animations just with Python, because it's going to be different for a one-dimensional scalar field versus a contour plot scalar field. The contour one is much more complex to animate. Okay, so let me think about that. I'm not going to promise you anything right now. Okay. So we will do, let's start by doing the visualizing two-dimensional scalar field. Okay, so visualizing a 2D scalar field. All right, so we will do both. We will do the 3D plot. Can I tell you something? I had never plotted a 3D plot in Python before because I know they're useless. So I had to Google it. How do I do a 3D plot, right? That's how committed I am to two-dimensional plots. Contour plot zealot. All right, so let's define the 2D Gaussian, defined bimodal Gaussian. Sorry, Gauss, I'm not going to capitalize your name because I have to follow case notation. And I'm going to give it x and y, and I put them in capital, and I'll explain why in a little bit. Okay? Because actually, okay, so let me hide. Okay, so this Gaussian function, let me get my slides. This Gaussian function, numerically, to be able to plot this, I have to have not just x and not just y, I have to have, so if I give it just only this x or this y, it's only going to give me the values along either this line or that line, right? Or sorry, this line or that line. But I want all the points in the middle as well. So I need to give it pairs of x, y values. I need to give it for this x all the y values, and then for the other x all the y values, and for the other x all the y values, and so on. See what I'm getting to? So to produce values of this Gaussian function on this entire two-dimensional xy plane, I need to give it a two-dimensional array of x and y values. Okay? So we can build that with Python very easily with a tool from NumPy. So before I define this function, let me create a new thing here. Okay, so before I define this in Python, let's kind of play around with this a little bit. I'm going to say I want number of points in the x direction is equal to 32 points, and number of points in the y direction, 32 points. So I'm looking at how many points I want to put on the x-axis and how many points I want to put on the y-axis to plot this. Okay? And then on the x-axis, I'm going to put a linspace, just a standard one-dimensional linspace, numpy.linspace going from 0 and let's say, okay, what did I do it here, until 5. So let's define Lx equal 5 and then Ly equal 5 as well. So on the x-axis, I'm going from 0 to Lx with nx points, okay? And with the y-axis, on the y-axis, I'm going np.linspace, going from 0 to Ly, also ny points, okay? So now that gives me x and y as one-dimensional arrays, right? X going from 0 to 5, and then y going from 0 to 5. Now, how do I create that two-dimensional array? I call something called mesh grid, np.meshgrid. So if you look at that, it returns coordinate matrices from coordinate vectors, makes an ND coordinate array vectorized. So what it does, you give it x, y, z, whatever, however many dimensions, and it goes and pairs them together and create all possible pairs, all possible combinations for those. Okay? So if we do np mesh grid, all you have to do is give it x and y. Now the return value is going to be two arrays. Okay, where's the return? Returns x1, x2, etc. vectors with lengths ni with these shapes for the, anyway, so what it does, it returns the pairs. It's a little bit annoying how they describe it. It's bad documentation, okay? So it returns all the possible pairs. So let's experiment with this. How about I do 4 points just so that we can see this, okay? So if I do just 5 points, so print x, I'm going to call this x. And you might have done this before. So just bear with me, please. OK, so this is x. I have 0, 1.6, 3, and 5, etc. So if I were to combine these together, I should have a 4 by 4 grid, right? I should have a 4 by 4 grid. Because for each value of x, I want all the values of y. So for 0, for x equals 0, I want 0, 1.6, etc., etc. Okay? How about we do, yeah, OK, so how about we change y a little bit so I get different values. Let's make y 4. Okay, so I have slightly different values so that you can see the truth here. np.meshgrid, I'm going to give it x, y, and I will store these in capital X and capital Y. Some people store them in x, x, y, y. So to designate that this is the grid. Either one is fine. Now I'm going to print x. So if you print x, it's going to contain, okay, all of the values. So for the first value of x, you have all of these values of y. For the second value of x, you have these values for y. Third value of x, you have these values. And fourth value, you have these values. Okay? And then for y, if I print y, is going to be the opposite. It's going to be all the values of x, first values of x, so the first value of y, all the values of x, all the values of x at the second value of y, and so on. Well, kind of the other way around, actually. So what I can do as well is actually do a contour of this one. So how do we do a contour? The simplest one is just to do PLT. Actually, can I visualize this? PLT dot IMShow X. Let me try this. Okay. So what this is showing me, if I do an image show, this is called an image show, it just shows the values in there. It's showing me that for each value, here I have a constant value just going up, but X is changing in that direction, okay? And same thing I can do in Y, and it's gonna go show change in that direction. The point is, I know this is not super clear as I wanted it to be, but X and Y, they give you these pairs. Now every two-dimensional function is going to take these X and Y value pairs. Okay, so now I can define my bimodal Gaussian on this. Okay. I can define, so if you remember the contour plot in the bridge oscillations, you had K values and speeds or whatever. On the x-axis you have the different theta values, and on the y-axis you have the different speeds, right? So you had to do a mesh grid on those to create all these pairs so you can do the contour plot. Okay. So for this 2D Gaussian, what I want is, let me see what settings I put here. And for my first Gaussian, I'm going to put x0, y0 equal, I'm going to put it at Lx over 3, and then Ly over 3. So I'll put it at a 1/3. I'm going to put it at 1/3 of Lx and 1/3 of Ly. Bless you. Okay. So let me move this down here so that we have Lx and Ly defined. Okay. And then sigma or Sx, Sy is equal to 0.5 and 0.5. Then my result is going to be np dot exponential, and I have the standard Gaussian. np dot exponential, and let's open up. There's a minus sign. I'm going to open parentheses, and then another parentheses. X, that's the mesh grid X, minus x0, correct? Squared, squared over Sx squared, so over Sx over Sx. So that gives me, and then minus, then on the Y, I'm going to, so let me check, okay, good. I'm going to open these parentheses, and then y minus y0 squared over sigma y squared, so over sigma y, and then I will close these parentheses. So that gives me the first Gaussian. Then I'm going to change x0 and y0. I'm going to move to the second one, and I'm going to put them at 2L over 3. So 2 times Lx over 3, and then 2 times Ly over 3. Okay, I'm going to keep sigma x and sigma y the same, and then I'm going to add this to result plus equal 0.5. So I'm going to cut it in half times, so let's copy this and paste it. This will be the same, right? So I had the first one, x0 was L over 3, and y0 L over 3. Say for the second one, I changed the x0, y0, kept everything else the same, and I added it to it, and then return result. Okay, perfect. And now that should just work out of the box. All right, so now let's do a 3D plot first. And normally I would just go to plt.plot, right? So we're going to do it all differently now. We're going to create a figure and set of axes and do PLT subplots. I know there's 100 ways of doing plotting in Matplotlib, and don't ask me, but this is the one I'm using for doing 3D plots. You can probably do just plt.surfaceplot, a 3D surface plot. But I had to do this time, projection. So I'm changing the arguments for this the argument settings for the plot, the standard settings. This is the last time we will ever use this, frankly, so don't worry about this. All right, and then we're going to calculate my z-values, which is bimodal Gaussian, and I'm going to pass on it x and y. Oh, did we delete did we delete the mesh grid? Oh, that was stupid. Okay, xy equal mp dot mesh grid x and y. Okay, there you go. All right, so I'm going to call it with this x and y values, right? And then we can do one of the x plot surface, and I will give it x, y, and z. So now this is the surface plot. Oh, it looks very, very, very ugly because I have 4 points. So let's do 64 points. 64 points. Okay, it's not going to assign color to it because this is not a contour plot. The height should describe the height of the surface. But it looks terrible, it looks ugly. Okay, so then you go and say, oh, let me add the color map. Or if you're going to add a color map, make it a 2D contour plot anyway. So the color map, we're going to do a CMap. Let me see. So do I have to include CM here? Okay. So here, what I had to import from matplotlib, import CM. These are color maps. All the color maps that allow you to do all sorts of colors. Okay? And you can Google like matplotlib color maps. There's a few that you would remember. And for this one, I used what's called CoolWarm, which gives you this kind of sharp separation between splitting at the 0 value, so red above 0 and blue below 0, and like white right around 0. So this would be called CM dot CoolWarm. All right, so if we do this, this is what you get. Okay? And this is exactly the same plot I have over here. All right, now we can do a contour. We don't need much to do a contour. For the contour, you do just x dot contour f, or contour f. F is for filled contours. If you don't want them filled, you just do contour. Okay, so we'll experiment with both. Contour f, we're going to give it x, y, and z. And if you do this, it's just going to produce something. Let's do plt.show, plt.show. OK, so I have to create a new figure. Sorry. Let me create a new figure here. And forget about this. And then, OK, so that's what it did. OK, now it looks wonky a little bit because it seems like it's kind of the figure size is weird. So you can specify the figure size. Let's do a fig size. OK, so we're kind of doing this here just for demonstration purposes. But once you go to write your first paper, real estate on a paper is very expensive. Sometimes you're limited by page size. You're paying money to publish this. So you have to be very frugal with your figure sizes. I like to use the golden ratio for all my figure sizes. Okay, so typically I go like 3/2 or 6/4. So length 6 on the x-axis, 4 on the y-axis. These are the actual in inches, or vice versa. Rarely do I go equal size, like 3/3. Just to break that, I do 3.15/3, just to give it a little edge on the x direction. There's a reason, because we typically read from left to right, but we scroll from top to bottom, right? So I want to limit it's really annoying to cut text as you're scrolling from top to bottom, but kind of you can read from left to right, but you cannot be generally more than half of your page size. So if you're an 8.5 by 11 page with margins of 1 inch or half an inch, right? So you only have about 6.5 inches to work with. So typically that sets the limit on the figure size to 3.25. So I would go 3.25 by 2 inches. Anyway, so as you write your first paper, now your advisor might have different rules in your field and your publications, but you will create very beautiful plots if you follow these rules. So, but here I'm just going to do, I'm going to do it 6 by 4, let's say, and fixed size is not defined, is equal, okay. Now that's my figure size, and I can change the color map. So in this case, I can do also, so CMAP equal, and this is different now, cool, warm, okay? So that gives me this one. But now let's say I want to put the color bar. So to call the color bar, I have to save the contour in a variable, and let's call it, my contour, and then plt dot color bar on my contour. Okay, and if I do this, it puts the color bar over here, but look how it squished the figure a little bit, so I'm going to give it an extra 0.5 over here. Sorry, I'm going to give it an extra, just change the aspect ratio a little bit, 5.5 by 5. Oh, that's terrible, by 3. Okay, that's a little bit better. Now for you to see what I'm doing, maybe we can just do it, like 8 by 6, just so you can see it better. Okay, by 7, that's too bad. 8 by 5, okay, that's a little bit better. Okay, now what if you want more levels on this? You can just specify here levels equal 20, or 20 levels. So it's going to put more color, but it starts to look cluttered. You see all of those lines in between, it starts to look cluttered. 40, 50. It gets really, really dense, and you start seeing this aliasing effect in the image. It's not very pretty. For levels, you can also specify the levels. You can say, I want level 0, level 0.1, level 0.2, level 0.5, and 1. It will only plot those levels, right? It will only plot those levels. Or you can put a linspace, mp.linspace, going from 0 to 1, and I want 10 levels. Well, that's going to be equal to just 10 levels. So when you specify levels, it's just going to do like something like the linspace, okay? Now, you look at contour, there's like so many options in here. You can really go down a rabbit hole. One important parameter or argument that we will need later is this value min and value max given by vmin and vmax. So here's the situation. Let's say I am looking at the decay over time of this pulse, and I'm running this through the heat equation. So from what we've learned in your current homework, I guess, this is going to decay over time. Now, for every time it decays, the min and max, the min is going to stay the same, it's going to be 0, but the max is going to change. It's going to go from 1 for the initial condition. After 1 second, maybe it's going to be 0.8. After 2 seconds, it's going to be 0.5, and so on. When you are trying to compare initial condition to somewhere in the middle to the last condition, make sure you keep your color map the same. Your min and max levels the same, so you have a valid comparison. Why? Because at after most of it has decayed, if you still color the highest as red, it's going to give the illusion, is this red the same as the red of the initial condition? No, they're going to look at the color map, well, it's a different value. That's kind of weird. Fix the color map from the initial condition or some condition that you think is useful from vmin to vmax. Fix those values. And then as it decays, you're going to see this peak go in more and more blue, 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 lower and lower into blue. Does that make sense? So that's where vmin and vmax will become useful. In the 1D case in space, okay, so let me go back to this animation, for example, this animation. Oops. Okay, this animation. Notice what I did. I fixed the y-axis, and then as it decayed, you saw that it was decaying. But if you were plotting without fixing the y-axis, what would matplotlib do? It would put a new bounds on the y-axis. So then as you animate this, it's going to be almost frozen in time. It's not going to change. So you fix your y-axis in 1D, or when you go to 2D and 3D, fix your min and max on the color map if you're animating things and you're trying to compare them together. Okay? All right, should we do the Taylor vortex as well? So we can do the Taylor vortex, this one, the same thing. Okay. Let's do the Taylor vortex. So define Taylor vortex. This is not GI Taylor for the, this is not the Taylor series guy. Sorry, not GI. This is GI Taylor, a different scientist. Okay. What is the first name of the Taylor for the Taylor series? I think it was Thomas. I remember we Googled that in class in numerical methods. Will someone Google that? What's the first name of the Taylor series dude? I think his name is Thomas. Brooke Taylor. Brooke Taylor. Oh, we had Brooke as well in the class. She was my TA, right? Yeah. Okay. Yeah. I remember, well, I remember there was a Thomas, other than the Thomas algorithm. But okay. All right, Taylor vortex XY. And in this case, I'm defining Kx, or K1, is equal. So this is going to tell me how many vortices I have in the x direction, and how many vortices, how many of these clumps I have in the y direction. K2 is 3, let's say. And then result is equal mp.cosine K1 times x plus mp.sine K2 times y. Okay, just very simple, one magnitude. And then let's do this again. Z, my new z. OK, so I'm going to change Lx, Ly, and Lz. I'm going to put new values here. Lx is going to be np dot, or 2 pi. We'll do it for 2 pi, or mp dot pi. And then mp dot pi, 64 points. Xy, lin space, mesh grid. Z is equal Taylor vortex, x comma y. And then we can do the same thing here, copy paste, 5, etc. And then we can z, where is z? What is going on here? Z, oh, return result, right? Didn't return the result. Got to return something. Okay, thank you, Mr. Python. Okay, so it did this, and I'm going to change my lin space. It's weird, my lin space, because the values go actually from -1 to 1, or -2 to 2. So I'm going to put 10 levels. There you go. Okay, there you go. It gives me this Taylor vortex. You can change the Kx and Ky. You can obviously play with the aspect ratios, do 6.5 by 5 and get a nicer looking one. If you change the K value in the Taylor vortex, these K values, you put 5, you're going to get more vortices, more of these cells. Okay, they're not really vortices. They're the stream function that are going to produce the velocity field. Okay. That are going to produce the velocity field. All right. We good? Okay. You probably know how to do this already, but it's a good exercise. Okay, let's continue. In general, we will write a scalar field. You'll see me write a scalar field like phi tx or phi xt, but x will be in boldface, or I can write it phi of rt. That designates the position in space. Could be xy, xyz, or x, just x. Just get used to that kind of notation. Okay? When you see phi or f of boldface x comma t, or t comma boldface x, x is a position in the space, 2 or 3D space. Okay? Now, generally, scalar fields are the solution of scalar partial differential equations, because we will have vector partial differential equations too. So a scalar partial differential equation, like the classic heat equation for temperature, there's a similar equation for species transport, for example. This would be, for example, a solution to this partial differential equation. Temperature changes in space and also in time. So when you solve this, you're going to have time and space in your solution, numerically as well. Next, we will talk about vectors. I don't need to remind you about vectors. They're well known, but I'll go through them real quick. A vector is really an imaginary bucket, and there's no vectors in reality. It's a model of reality, right? But we notice that, like the velocity vector, okay? It's determining my speed. So if we take this as the x-axis, this wall as the x-axis, and this wall as the y-axis, if I go in this direction, I only have one component of speed in the x direction. I need one number, right? And if I go in this direction, I need one number to describe my speed. But if I go in this direction like this, I'm going to need two numbers to describe my velocity. How fast I'm going in the x direction, how fast I'm going in the y direction. Now, physically, there's nothing special. It's not like I'm not feeling the velocity in the x or y, right? But they are related to each other. So my speed, the way I sense is just from my perspective, there's no x and y. It's just whatever direction I'm going. But as observers, as we're looking at me moving, you can rationally say I'm moving this much at this much speed in the x, at this much speed in the y direction. So they are related together. It's not like randomly we pack them, we pack the x velocity and y velocity together into a vector. They are related to each other. So vectors, they will describe things that are related to each other, okay, physically, in physical space, in real space. And we describe them as, either you can put them as a row vector like this in parentheses, giving the components of each direction, the component in each direction, or you can put them as a column vector, or the way I really like is using an algebraic way of writing this, where you put the first component times the first direction unit vector plus the second component times the unit vector in the second direction. So if E1 is the unit vector on this wall, which essentially is just something pointing in this direction that has unit length, and E2 is the unit vector on that wall, that tells me I'm going U1 in this direction, U2 in that direction. That will be my resultant vectors. This is classic vector stuff, right? Now, what's cool about vectors is that they are like dandelions. They grow and live anywhere. So this is a very, I know it's such a silly point to make, but it's very important. When people tell you, oh, you can translate vectors anywhere you want, that's true, because when you have a vector, you know, when you're adding two vectors, one of them, sometimes, you know, your teachers would trick you. They would put one vector like this and one vector like that. Well, you just move them to the same point at the origin, or whatever point you want, and you do the addition. It will result in the same vector. They don't care where they are, right? Now, once we look at flow fields, for example, you're going to say, like, my flow field velocity vector at that point in space and time is going to look like this. But you can still, you can't say that the speed, I can move the speed anywhere I want and say the speed is different. No, that would be wrong. But if you're making vector operations, you can move the vectors anywhere you want. That's convenient to you. Just add them or subtract them from each other or curl them. The same way we define elementary. Has anyone taken group theory in math? Okay. If you want to, like, not waste time, if you have a course to spend, go take a course in group theory, because it will blow your mind away. Group theory is like the tuning fork of mathematics. It is, in group theory, we look at everything, vector spaces, numbers, complex numbers, quaternions, etc. We look at them as objects in math, and then we define operations on them. So in group theory, fundamental operations are addition, subtraction, multiplication, and division. Okay? When we look at the vector spaces to see what kind of groups they form, okay, what kind of properties they have, are they commutative for addition? Are they commutative for multiplication, etc., and so on? So group theory will help design those questions, answer those questions. So we need to define vector addition, vector subtraction, vector multiplication, and there's no vector division. Okay? So we have to define what we mean by those things. Addition is very easy. You can define vector addition by simply adding the components. Okay? Adding the individual components in the x direction, adding the components in the y direction. That gives you standard vector addition. Now, if you've taken group theory, you can define a different kind of addition. You can say, I'm going to define addition as taking the square root of each component and adding them together. And you'd give it a different symbol, okay? But it will not result in something necessarily useful. So this kind of addition on vectors will result in certain properties. Vectors, they become invariant in space and so on and so forth. Right? But you can define other things. So that's the reason why we define the dot product in a certain way, or we define the cross product in a certain way, so that we keep vectors to stay invariant, etc. You can define other products, but they're going to break the rules on vector spaces. Okay. So classic vector addition, you can subtract vectors as well. Next definition is something about the vector product. The first type of product we define on vectors, which is the easiest product, is called the inner product, or simply just the dot product. The dot product is simply taking the product of each component pairwise together. So you take A1 times B1 plus A2 times B2 plus A3 times B3 and so on. And that just gives you a number. Okay? The dot product of two vectors, we're going to explain what it means in a second. But it always results in a scalar value. So you're downgrading vectors to a scalar. Okay? So if you think about things we've seen, you get scalars, vectors, and then there are tensors that are higher order vectors. We will touch on tensors a little bit later, but not now. But the dot product downgrades a vector. You would expect like when you multiply two numbers, you get a number. Right? You don't get nothing, you get a number. Okay, why is multiplying two vectors not giving me a vector? Well, because this is a special type of vector product called the dot product. It gives you a number. Okay, so be careful. So keep that in mind because we need to distinguish what we mean. Now, what does the dot product measure? What does it measure? Go ahead. How parallel they are to each other? Okay, so let's build on that. So I have a formula here, another formula saying that the dot product of A and B is the magnitude of A times the magnitude of B times cosine theta. Now, if I were to project this A on B, what would I get? I would get A cosine theta. If I were to project B on A, I would get B cosine theta, right? But this one is somehow combining the two, A times B times cosine theta. It's measuring how parallel they are. So if they're not parallel, what does it do? If they're perpendicular, what happens? 0. And if they're fully parallel, the maximum value, right? So indeed, the dot product measures how much two vectors are parallel to each other, or a different way of saying it, how much they point in the same direction. Okay, just because if the two vectors are parallel, the dot product is a maximum. Okay, it could be positive or negative if they're pointing in opposite direction, but it would be the maximum value. And then they are pointing, they are parallel to each other. And if it's positive, they're pointing in the same direction. If it's negative, they're pointing in the opposite direction. And when they are perpendicular, they are 0. It's 0. So they're not pointing in the same direction at all. Now this is a very useful property. Okay, this product gives us a very useful property because we will use this later to infer things on when we use the divergence with these things. If the divergence is 0, it has a certain meaning. If the divergence is positive or negative, it has a different meaning. Okay, so keep that in mind. Now A dot B, and this is what I said about dandelions, and you can move them whatever you want. So if I were to give you A dot B like this, what do? You just move this vector, put it here, and then do the dot. Just kind of move it and put it here, and do your dot product. What about B dot A? B dot A is equal to A dot B. Okay? It's commutative. The dot product is commutative. A dot B is equal to B dot A. it gives you the same number. Okay, there's another multiplication. So that's one multiplication, which was weird. We took two vectors. We didn't get a vector. We got a scalar. There's another multiplication that gives us a vector, and that is the cross product. It's a different type of product, also defined in a certain way to preserve certain properties about vector spaces. The cross product of two vectors, I'm giving this in general 3 dimensions. That's what we are going to limit ourselves to. And the result of the cross product is written by this multiply, x. The magnitude of it is similar to the magnitude of the dot product, but it has a sine theta instead of a cosine theta. So what was true for the dot product properties, the opposite is going to be true for the cross product. So we said the dot product is maximum when they're parallel and 0 when they're perpendicular because of that cosine. The sine is going to flip that meaning here. Okay? When they are parallel, the cross product is going to be 0, and then when they are perpendicular, the cross product is going to be a maximum. Okay? Now, the cross product results in a vector, and that vector is given by the determinant of this matrix. In different coordinates, we can build this differently. We're not going to dig deeper into different coordinate systems. We'll do a couple of examples later. But you can do the determinant as you would do just a standard determinant on a matrix, where you take now, you go, you start with the I direction, and then you kind of blank this down out, blank this out, and then you do this A2B3 minus A3B2, and then minus J, you block out this column and this row, and then you get A1B3 minus A3B1, and then plus K, etc. So it gives you a vector with 3 components, right? Now, if you were in 2D, for example, if you were in two dimensions, you would have just I and J, right? So you do the same thing, okay? You would have I and J, and you would do the same thing, and you would get a vector. Now, the interesting thing is that, like I said, the properties of the cross product are going to be the opposite of the properties of the dot product. So this is going to be super useful later when we get to differential analysis. Because the equivalent of the dot product was, I called it the divergence when we do vector calculus. The equivalent of the cross product for vector calculus is going to be the curl of the A vector. Now, the cross product is a maximum when A and B are perpendicular to each other, and it is 0 when they are parallel. So then that's an important property. If you're like computing, if you want to design a vector that is parallel to another vector, and you're like, you want to do the hard way, okay, you build a vector whose cross product is going to be 0 with that vector, so you get a parallel vector. Or if the result of the cross product is 0 or close to 0, you know that these vectors are almost parallel. Now, what is the direction of the resulting vector from the cross product? The right-hand rule, if you're left-handed, I don't know how to do it. Maybe you can help. If you're left-handed, it's going to be the opposite. Okay, take the opposite of what I'm saying. So what do? You start with the way I like to do it. I start with the, I draw my A and B vectors. I'm doing cross product of A and B. I start with A. This is my thumb. I keep it pointing up. I start at A, and then wrap my hand around to B, and it's going to be pointing out. So if A and B were in the plane, the resulting vector is going to be pointing towards you. If I did B cross A, I have to do my right hand. I have to start at B and then curl to A, and then it's going to be inwards. So A cross B is not going to be equal B cross A. It's going to be the opposite of that. Okay? So the resulting vector of the cross product is a vector that is perpendicular, okay, that is perpendicular to A and B. So if A and B were both in the plane, the resulting in the xy plane, the resulting vector is going to be pointing away from them in the k direction, right? Well, that's what the interesting property about the cross product. The magnitude is given by this thing, A times B times sine theta. That's just the magnitude of the vector, okay? And A cross B is minus B cross A. Unit vectors are essentially vectors of length 1 The easiest are in the Cartesian space, I, J, K, or EX, EY, EZ, or E1, E2, E3. Sometimes you'll see me put a hat. Sometimes I don't put a hat on them. All of this is allowed. You should just be able to know that this is a unit vector. It has components. In the I vector is 1, 0, 0. So value 1 in the x direction, 0 in the y, 0 in the z direction, and so on and so forth for j and k. And then you can start doing these properties about these unit vectors. So I dot I, you're dotting the same vector by itself. It's going to give you the maximum value of that because it's parallel to itself. It's going to give you the maximum value. It's going to be 1 in this case. But if you dot unit vectors with the other orthogonal unit vectors, they're 0 because they are perpendicular to each other. So that's what we expect from the dot product. Okay? Okay, so the same way we defined scalar fields, we can define vector fields. Okay, and now this is going to get a little bit, this is where it gets more complicated. If you take this vector, and so I had to write, I forgot the unit vectors here. My apologies. Let me fix that right now. Let me fix that. Okay. So okay. Okay. So if I have, this is a vector field. So it's a field of vectors. So at every point, I have a vector, 3 components, 2 or 3 components, or 1 component. And those vectors are changing in time and space. So all possible combinations you can think of, okay? So if you think about it, if you had the 2D contour plane that we had, at each point, I'm going to have a different arrow, very simply. And those arrows can change in time. They can grow and shrink, and they can spin. Okay? At the same point, they can spin, or they can grow and shrink in time. So the way I would write this is u vector, so that's boldface of xt. Remember, x is a position vector that gives me the point x, y, z in my physical domain. And that consists of 3 components, u1, u2, u3. u1 is the x component of u, and it's also a function of x and t. So it's a function of x, y, z, and t. And that's only in the I direction. Same thing for the second component in the y direction. It's a function of x, y, z, and t. And same thing for the third component. So that's the only way you can get a total vector field that changes in time and space if each component changes in time and space. To demystify this, think of each component as its own scalar field. All right? Each component is a scalar field that changes in space and time. Combined together, you're going to build a vector field. Now, you have to build them. They have to be related. You cannot just randomly put scalars together and call it a vector. It might not be invariant, etc. So a vector needs to come from a truly physical property like the velocity field, etc. Okay? So that's why I like to distinguish between arrays and vectors, so to not confuse the two. Okay, the next step is going to be vector calculus. And with vector calculus, the minute you hear the word calculus, you're talking about integrals and rates of change. Okay, so we'll start with differential calculus. And the fundamental operator for vector fields in vector spaces is this symbol. Some people call it nabla, some people call it del, some people call it the grad operator. Use whichever you want. Del or nabla are more interesting. The nabla operator, interestingly, so you'll enjoy this, comes from the Greek description of a harp that looked like a nabla, so you can Google this, which they think the Greeks called it from the Phoenician, the ancient Lebanese, or the Egyptians, or the Iraqis. So they think there is a history there of that. Call it al-nabla, and so al-nabla, and so it comes from that because it looks like it. Okay, it looks like it. And anyway, so call this operator nabla or the del operator. It's an operator, so it needs things to operate on. Okay. Now, what is it doing? So it's like a machinery. You feed it something, and it does something on it. Now, we will see we can feed it scalars or vectors, and we're going to get different results with that. But in and of itself, I like to think of the nabla operator as a vector. Okay? Think of the nabla operator as a vector. And it has three components. They are partial derivatives, derivative with x in the x direction, derivative with respect to y in the y direction, derivative with respect to z in the z direction. It will differ in different coordinate systems. Okay? We will see those later. But for the simplest Cartesian coordinate system, this is what it is. Literally, it's d by dxi plus d by dyj plus d by dzk. By itself, it's foolish. It doesn't do anything. It's an operator. It needs something. Where is that thing going to plug in? It's going to plug in the derivatives. Okay, so if I say nabla of something, that something is going to go, the whole thing is going to go in the derivatives. We're going to define different ways of using nabla, but think of it as a vector because that's a trick to be able to understand later what gradient, divergence, and curl are going to mean if you think about nabla as a vector. Okay. Nabla is a linear operator. So for example, if I do nabla of alpha f, and f is a scalar field, remember nabla is an operator in x, y, z, and f has to be a function in x, y, z, or if it's an x and y, it's going to be in x and y. Right? So nabla alpha f, and if alpha is a constant, this would be alpha nabla f. Nabla of the sum of two scalar functions is going to be the sum of the nablas of each scalar function. Okay? So that's the simplest linear operation on nabla as is. Once we define other operations on nabla, we have different linear properties. Then we can define a variety of operations between nabla and scalars and vectors. First, we will look at the gradient of a scalar. So remember this very, very well. The gradient always operates on a scalar. Can you have a gradient of a vector? Yeah, it's called a tensor. We don't have to worry about that right now. But the gradient of a scalar, okay, gradient by definition, it operates on a scalar. The resulting of the gradient of a scalar is what? A vector. So you take a scalar field, you plug it into nabla, and you just simply write nabla f, or say grad nabla phi or grad phi. The result is d phi by dx in the I direction, d phi by dy in the y direction, and d phi by dz in the k direction, or this vector. So we've taken a scalar field, applied the gradient operator on it, or the del operator on it. The gradient of a scalar is going to be a vector given by this result. Okay, now phi is still a scalar field, x, y, z, and grad phi is also a vector field. Okay, it changes in time and space as well. All right, so what does grad phi mean? What does grad phi mean? Okay, but it's a vector, right? Like, what is it? The vector points somewhere. What is it pointing towards? Okay, the direction of the highest rate of change. Okay, so think of it, take a simple one-dimensional example, df by dx. It's essentially a vector in one dimension, right? I have one function, phi f, and then take df by dx, and suppose you're going up a hill, and then you're going down. Okay, so vectors in 1D, they can all either point in the positive x or in the minus x direction, right? In 1D, so this is a 1D curve. So as you are traversing the curve upward, df by dx is positive, okay? So the vector of df by dx is pointing in the positive x. Now you go to the other side of the hill, you're going down. df by dx is what? Negative. So the vector is going to be pointing in the negative direction. Towards what? Towards the peak of the hill. So the gradient, by the same token, the extension in 3 dimensions is that the gradient vector, the arrow, is always telling you where to go, where the hill is. And we're going to do a couple of examples. We don't have much time, but let's do the 1D example, at least the 1D example in Python. Okay? So then I'm going to create a new notebook. And then I need to run to the other class. Okay. So move to Creston. So we'll revisit this next time, okay? We'll revisit this next time. I'm going to copy and paste this. Okay, so what I want to do now, just kind of show you what the gradient looks like in one dimension, okay, in one dimension. I'm going to define bimodal Gaussian, but this is 1D, okay, 1D. A 1D bimodal Gaussian, and then A is 1.0, sigma is 0.3, and then x0 equal, or x0 is equal 1, and then x1 is equal 3. So I'm going to put a bimodal Gaussian with a hill and then a trough. And I want to see if it's always going to point in the direction of the larger value. That's kind of what we anticipated, right? If it's going to point in the direction of the larger value, okay? All right. Then return a times np dot exp minus x minus x0 squared. So that's going to be the first peak over s squared, so over s, right, minus 0.5. So actually just minus 0.5 times, let me copy this, oops, and minus x1 over here, squared over s, okay? And then x is mp dot lin space from 0 to 5 with 200 points, then plt dot plot x bimodal Gaussian 1 dx. Okay, so this is what this looks like, plt dot grid. Okay, this is what this looks like. So what I would expect is that, so df by dx is positive here. The vector made by df by dx is going to be df by dxi, right? So it's going to point in this direction. Whereas over here is going to be negative, is going to point in that direction, right? Here I'm descending, it's also going to point in that direction. But look what happens here. Once I hit this trough here, this is going to be ascending, is going to point in this direction, because locally the closest hill to this one is this guy, not that guy. Okay? So it's always going to be local. Okay? It's always going to be local. We will do the gradient in 2D on Thursday. Okay? So we will make the 3D Gaussian, the 2D Gaussian, and then we will put the gradient on top of it and put the vectors and see where the vectors are pointing. So this gradient is very, very important in optimization and machine learning. Gradient descent algorithms, they look at the gradient, they follow the direction of the gradient, because the gradient is always pointing you in the direction of the largest local value. Okay? That's where you find maxima, and the opposite is true to find minima. Okay? Thank you. I'll see most of you in Intro to Research. Thanks.